still cold outside, so indoors here. It's January 9th, 2021. We make these videos usually ahead of time for classes that are coming up, in a few weeks. And this is class here I, quantum mechanics. And we're going to show you where the Schrodinger equation comes from. Now, this is, remember, when we say derivation, we mean that we're going to show you some relationships, show you how to arrive at the Schrodinger equation. And this is not the traditional treatment. In fact, usually the Schrodinger equation in quantum mechanics would be just stated or given, just like you would give F equals ma, say, as a basic equation in the classical physics. But we're going to show how to do this, inspired by my mentor and teacher, Dr. Richard Houston, when I was an undergraduate, who said that the backdoor entrance in the quantum mechanics from classical physics is, now before I tell you, can you think of anything in classical physics where there's discrete jumps? You can't have anything in between, all right? You can pause the video and think about that for a second. Like the energy levels of the system is not continuous. Well, this is a tough question and very, I think, difficult to arrive at an answer. And the answer is the harmonics, the vibrations on a string, that you have the fundamental, and then you jump an octave higher for the second mode, and then 3 times the frequency is the third mode, and you don't get the cases in between. So you can think of those as energy levels like in chemistry. They jump. And we're going to use that technique to arrive at the Schrodinger equation. And when we find that solution and use the de Broglie relationship to, and some things involving quantum ideas, that the energy of a particle is h times the times f, and the de Broglie relation will show you that we have a solution that we're going to then find a differential equation for. And when we find the differential equation, we run into trouble. We will need to introduce the imaginary number I. So you can consider this. Also, the question is, why is I needed in quantum mechanics? In fact, once a professor at the University of Maryland titled a talk that way, and everyone came, but then they didn't understand what he was talking about because he's very advanced. Actually, this class will show you why I is needed in quantum mechanics. All right. So I hope you enjoyed this class. This is a very fundamental equation in the realm of the microscopic, or the small realm, where things travel at a slow speed. Quantum mechanics. Chapter I. Quantum mechanics. I1. Quantization. In classical physics, we're used to having things that are continuous, like you can go any velocity, speed, you could have any energy. And in quantum mechanics, we find that that's not the case, that there's quantum effects, like quanta, like discrete lumps of things. And the first one that we're going to look at is the quantization or quantizing oscillator energy. Now, this occurred here, this is 1900. And remember the harmonic oscillator, the force is minus kx, F equals ma. And we get oscillations. I'm going to make a little circle here and let this represent moving back and forth, and that's our harmonic oscillator. And to understand data that was being observed at the time, Max Planck, here's Max Planck, he quantized the oscillator energy. So here, if we look at, say, the energy in, remember the harmonic oscillator had potential energy 1/2 kx squared when we did the work on, kx and did the integral, we got 1/2 kx squared. Well, see, this is a continuous variable in classical physics. But what Planck is saying is that that energy, these oscillations in the oscillator, would have energy En, where n is a number like 1, 2, 3, just a counting number, and you have here the Planck constant named after Planck, and the frequency. So the frequency of the oscillation, given by, you may recall, we did this problem already, omega naught is square root of k over m, and this is related to the frequency. It's called the angular frequency, and we'll talk about that in a second, that these are the energy levels. And that described the data when they were looking at, say, the glowing light that comes from a kiln, the so-called black body radiation. And when we look at quantum mechanics in 1925, the energy for harmonic oscillator is very, very similar equation, except that here n starts off at 0, but still when you have a delta, n here by 1, you have an hf. So, the delta is still hf, but in quantum mechanics, when n is equal to 0, you have a ground state energy. So when we looked at, say, PV is nRT, and we said for absolute temperature, when you get to 0, then pressure is 0, and since pressure, temperature is related to kinetic energy, motion, that all motion stops. That's not really quite true. With quantum mechanics, you would be in the lowest energy level. In the case of a harmonic oscillator, it'd be the 1/2, the ground state would be the 1/2 hf. And then what Planck said is when the oscillator, the walls of a kiln, so you can think of a glowing kiln, like for firing sculpture, that you would get, say, energy would come off the change, from adjacent ones would then be, if you went from the n plus 1, to the nth, that would be the delta, that would be your hf. And the radiation, see, that would describe the light coming off, could explain the observations. Now, when you get to Einstein is next. This is quantizing light. I mean, technically, he's quantizing the oscillator, but Einstein is going to take it a step further and say, actually, the light that goes off when you go from 1, say the n plus 1, down to the nth level, that you shake off, see, a photon. Now, a photon, that name came later, 1926, by chemist Gilbert Lewis, who coined that name, and we use that name. And Einstein used this. He used this to describe the photoelectric effect. So we're saying here the energy of a photon is hf. There's Albert again. Now this is 1905, the year of special relativity, but he's going to get the Nobel Prize for this other discussion that is involving the photoelectric effect. And the way the photoelectric effect works is that if you have, say, a metal and then See, light goes on, you shine light on a metal. If the light should have, say, near the blue end or even beyond, depends on the metal. Say if you had ultraviolet light, then you kick off electrons. Electrons get popped off the metal. But the mystery here is that if you had just, say, red light, because remember, if you have the Roy G, BIV going this way, that's, where your frequency increases in your energy. So a lot of folks will just, do it this way. And this is the increasing energy short wavelength. So if you had a lot of red light, nothing would happen. But if you get to like violet or say ultraviolet, depends on the metal, then you start kicking them off and you don't need much intensity. So if the light was a wave, you would just say the tidal wave should do it, like more red doesn't do it. So that's how Einstein explained that light came in packets and the energy was greater for the ultraviolet, because see the frequency increases going to the right, right? G BIV UV would be here. And you need to have a photon with more of a kick to get the effect. So Einstein explained the photoelectric effect, which you'll study if you take modern physics, and this is a little more detail I have in the book, but for our purposes, the idea of quantizing light is what we want to mention. And then 3, quantizing angular momentum. So that's a common theme, say things are quantized, the idea of quantum mechanics. And this is 1913. And this is Bohr and Rutherford working together on this one. And it's commonly referred to as the Bohr model. So here, the Bohr model, you have energy levels in hydrogen. Say this is hydrogen, and the levels get bunched up like this. So if you have the ground state, 2, 3, and 4, and then when an electron drops down from one level to another, a photon goes off. And Bohr said that when the electron is in orbit around the proton, it doesn't radiate, because see, you would expect acceleration, you would radiate, and then it would spiral in, and you wouldn't even have an atom, you wouldn't exist. But he says it didn't happen. Only when you have a transition, it happens. So then the delta energy is, you can look at it as here as a difference. You take the difference of the energy level. So if you had here, for example, see some higher energy level, and you went down to some lower energy level, then you would give off a photon with the energy reflected in that frequency. So if it's a greater drop, it'll be a lot more like ultraviolet, and if it's not as great, it'd be visible or infrared. So to make this work, the momentum is mv, and when you have a simple circle idea, the angular momentum is mvr. That's your angular momentum, which is defined in intro physics courses, and we'll just define it here. So when you do that, Bohr said this is quantized, and he said it comes in little chunks, n times h over 2 pi. And we call that combination h bar, and that's the Planck constant. So angular momentum is quantized. Niels Bohr is very special to me because of a line of teaching, and it's special to you because with Bohr, he had a student, Wheeler, who then had a student, Misner, who taught me general relativity at University of Maryland, and then I'm teaching you. So let's go on here to I2 and look at modern physics again that we've talked about. Modern physics revisited. Remember our little diagram here, large, small, fast, slow, classical physics here, relativity here. So this is your speed, and this is your size, getting smaller. And then this is a Planck constant, and it's introduced in here with this de Broglie relation. You get this Planck idea, and then Dirac. So modern physics are these two areas, and we're looking at this one today, down in here. But before we do that, let's look at relativity. If we look at relativity, we have the cool triangle where if you put, say, mc squared here, that's the rest energy where a particle's not moving. And then here, if you have some motion, then you get an increase in the energy. You can think of it as like kinetic energy is kicking in, but your general formula is E squared is m squared c to the fourth plus p squared c squared. Now we said that for light, you can think of the 90-degree angle where the energy is all pc. Because as this gets faster and faster and faster, your angle increases. So therefore E equals pc for light. But we also have the equation E equals hf, which we saw with the photon, Einstein. Then if we set these equal, we get pc equals hf, and we looked at this before. And then if we notice that the speed of light is the wavelength times the frequency, that's the how you relate those two together. If you have the wavelength here, and say the wavelength, let's just give you an example with just a water, like a water wave, 10 meters, and I'm just making this up. And then here, if the frequency is 5 per second, if 5 go by per second, then the speed would be 50 meters per second, because 5 of these have to go by per second. So you're watching here and them go by. And that's obtained by multiplying the wavelength times the frequency. So that's the formula, wave relation. So this means we have P lambda F equals HF. So the F's go away, and you then get this nice result that the lambda is equal to H over P, which is the de Broglie relation. When he wrote that down, he said that applies for matter. Like matter has a wavelength. And here is de Broglie. Matter waves, that this applies in general. So this brings us to two big surprises. So we have two big surprises. One surprise is that light, which was thought to be a wave, classically, light is also a particle, photon. Two, particles, matter, classically are thought to be particles, like bits of things. Particles also wave, are also waves. So we have here a wave-particle duality. So surprise one, light is not only a wave, it's also a particle. But then particles, surprise two, are also waves. So in other words, everything, particle wave. Now it would be nice around 1930 if life were this simple. But if around 1930, we knew about the proton, the neutron, well, actually 1932 really, but approximately 1930, close enough, and the electron. And neutron's neutral, and proton, and I'll just pull a minus sign like electron, a lot of times that's done. And then here you have pure energy, light, the wave, form without matter. So to be nice, you have four things. Like the Greeks many, many years ago said you had, for example, I'm going to call this, as one of my instructors at the University of Brown called it, the Waif theory of matter, that the world has four flavors: water, air, fire, and earth. And today, of course, we know that that's not really correct, but you might say it's one of them's right, because we would accept fire for light. So that's close enough. We'll give them that. But now we know there's chemistry, the rich chemistry, proton, neutrons, and electrons, say, and photon, and then this gives us the rich variety of all the elements. But life is not so simple. In the 40s and the 50s and the 60s, when they smashed particles together, they got lots and lots of particles, dozens and dozens. So that gets us into quarks and other stuff. So we will just say life was simple back in the old days. Well, almost. I mean, there were still problems. Neutrino was popping up and things. But if you could sweep a couple of those things under the rug, these would be the big four. Okay, so that gets us our modern physics, the Brillouin relation and the speed of light being constant in all the frames of reference. And that just never ceased to fascinate me, that speed of light can actually be written in terms of the constants of electricity, epsilon naught, and magnetism, mu naught, actually is written in terms of constants. Amazing. And Einstein, of course, said it is a constant. Like C actually is a constant from all frames of reference. Inertial frames in 1905, and then in general relativity, all frames. I3, wave properties. It would be nice to make sure we all have an understanding of wave properties. Now, we looked at the waves before when we had light waves, and we said a simple wave is one that has an amplitude. I'll put A there, but it could be electric field amplitude or a magnetic field amplitude, for example. And then we had the sign. Now we explained that we needed to have a K in there to make this dimensionless. Since the sine of X, if you put here sine of X, or in this case, we'll just say sine of U, since we already used X, that has to be like a pure number. And this is a wave moving to the right because it's of the form a function of X minus Vt. So waves that move to the right are going to have this form. And if we were to look, say, at the sine wave, and say we have this sine wave here, and we could like look at that. But if we look at this sine, let's say this is sine of U, and this here is a U. All right. Then if you look at this distance, see with the sine wave, the pure math, you're looking at a 2 pi here. That's 2 pi. Saying this is pi, and that's the 0. Saying that this over here would be negative pi and negative 2 pi. So the mathematical function here, when you apply it to physics to get your wavelength, you're basically saying that if you look at this thing in here, and what we'll do is we'll take t to be 0, so that we're taking a picture, a snapshot, and say that's like the picture when t is equal to 0. All right. That's an easy way to think about this. Then you have here the sine of kx, all right, because u has simplified now since t is 0. And then if the k times the wavelength, you put the wavelength in, then you have to get 2 pi. So that gives us the formula, it tells you what the k is. The k is 2 pi over lambda. And that's nice to know that as part of the properties of waves. And then what we can do next, that would be let's go ahead and call this section that we're looking at here, let's call this discussing the wave number, because that's what that K is. The K is the wave number. And the reason why it's called the wave number, because if you had, for example, like, mathematically, if you had sine of 2x and did that, then when you look at the sign, when you get x is pi, you already have a 2 pi, you already have one cycle. And then if you have 2 pi out here, it's 4 pi. So in other words, if this is, we're just pi 2 pi, let's do it like that. So if x is pi, then the sine of 2 pi is going to get you one cycle. And if x is 2 pi, since you have a 2 there, you're really at 4 pi. So that means in this 2 pi, you have two waves. You have two waves instead of one. So that's why it's called the wave number, whatever that is, like 2. If you had 3x, then there'd be 3 wiggles in there. So that's the wave number. Then 2, the angular velocity. And these are covered in physics courses, but physics is not a requirement for this course, so we should at least spend a few moments talking about that. And for the angular velocity, you're going to let x equals 0. So we have now the sine of minus kVt. We're staying at the origin, watching a wave go by. And here, if you wait so that one cycle goes by, that would be, the analogous would be there, k times vt would have to equal a 2 pi. And that's like one cycle, because when you ever have 2 pi, you went through one cycle. Here you have a time thing. So when the little t is capital T, and that's called the period, up here, that one's called the wave length. Then here, you can look at this formula as kV is 2 pi over t. But see, the frequency is always 1 over t, because if it takes you 3 seconds to do something, then the frequency is doing 1/3 a second. Or if it's taking you, say, a half a second to do it once, then you do it twice a second. So this is sort of a common sense, this definition. This has to be true, all right, by our definitions of frequency. You do something here, let's say if you do something 10 times per second, then that means the time to do one is 1/10 of a second, say. So therefore, this is 2 pi times f, and they call that the angular frequency omega. Like how many 2 pi radians, how many circles you're making per second, the angular frequency. So you have kV equals omega. And that means when you write down this equation here, A is sine of kx minus vt. Since the kV is the omega, a lot of times we can see this written as kx minus omega t. Like that's another way of writing the basic sine wave. Nice result. Okay, now we go to I4, which my mentor at my school in Philadelphia as an undergraduate went to St. Joseph's College. Now it's called St. Joseph's University. He said that there was a back door to quantum mechanics from classical physics, the back door to quantum mechanics. In other words, what can you think of in classical physics has discreteness in terms of energy levels? And the answer is the vibrations on a string. In other words, you have this one, the fundamental, and then if you go to the next one, this one goes at a faster rate, but you don't get anything in between. And then the third one, if you mark off, say, thirds, then you get this kind of a wave. And this can be easily demonstrated in class. and I do that for my general students that don't study math with physics, and we just shake this string. Well, it's actually a spring, like a $15 spring or so. We just shake the spring, and we get these effects. And there's nothing in between. It's like chemistry, energy levels. You're in this one, the ground state, then you're excited, you're doing this one, more excited, nothing in between. So this is the secret. We find something in classical physics that has discrete levels. Let there be music. Since these are the vibrations like on a violin string that give you the harmonics, a distinct set of frequencies. And then you could use the harmonics to analyze periodic waves according to Fourier analysis, which we'll look at later in our course. So here, what's the secret? Well, if you look at this, I remember having a teacher at the University of Maryland that called these humps. Here's one hump, here's two humps, here's three humps. And then when I was writing a paper on relativity and quantum mechanics up in this area, we were using a harmonic oscillator to write a paper. We were getting waves that had this similar property. And I remember my advisor asking me for the paper I was writing, like what to call these things. And I says, well, a professor I work for calls it the hump, but he didn't think that was a good term. So he asked Misner in our line of teaching. Remember, Misner taught me general relativity, and then Misner's teacher is Wheeler, who had a teacher of Bohr. And Misner said you should call it a half wave rather than a hump. So that's a half wave. So it's a half wave, and you can think of that as a half wave because it's only a crest, and a wave has a crest and a trough. So if you had the crest and the trough, this wave length is actually 2L. Now this one fits perfectly, but see, the rule is, here is a half wave, here are two halves, here are three halves, and the next one would be four halves. So the rule is N half waves have to equal L, and that's the quantization. In other words, you're quantizing the wavelength. The wavelength can't be anything. Can't be anything in between. And this frequency here, when you go to this one, this actually doubles the frequency, and this is triple the frequency. And there's no frequency in between, F and 2F. So this is the wavelength that you get is quantized, 2L over N. And you could actually put a sub N there for the different levels. Now, if we use the Broglie relation that we already looked at applies to matter, then we can put this wavelength in down here, and this would then flip. This would be NH over 2L. So 1 over lambda is N over 2L. So if you want the 1 over lambda, put the N over 2L, and then you have this relation. This is very, very cool. All right. Now, as we go to apply this to quantum mechanics, we're going to say that there is a wall and there's a particle that's bouncing back and forth off the walls. And we're going to quantize the energy based on this classical quantization for the various harmonics. All right. So if we do that, we know that this is a free particle. So therefore there's just kinetic energy, and that's 1/2 mv squared. And remember, you can always write the energy with this cool trick. You can put an extra m in the numerator and an m down there. So it's like the same thing, just like divide by m. And then since the momentum is mv, then you write this as a cool p squared over 2m. That's real neat. So now we're going to put this in here, and we're going to have quantized energy levels, like for a particle trapped in a box. In fact, this is called in quantum mechanics the infinite square well. Infinite square well. If you had like a potential energy in X, it'd be like this would go up to infinity or something, so you can't get out. The particle's free in here, going back and forth. And out here, in potential energy go to infinity, and you're not going to get out. So that you'll be studying that if you take like modern physics and quantum mechanics, but you don't need to. I'm going to show you here the equation for quantum mechanics in a second. By doing this, we then going to square this stuff, so that's n squared h squared, and then we need to square the 2, the 4, l squared, and then we have the 1 over 2m down in there. So when we do that, we get for the energy, and if you want, you can say it's the nth energy level, there's nothing in between. It's n squared, Planck constant squared. Notice how that Planck constant shows up in equations for quantum mechanics and the quantum realm, just like C shows up in the relativistic realm. So you have 2 times 4 is 8. You have m l squared, and L is the width here of between the walls. We're just saying L. Remember, I called that 2. I should have given you L in there as a definition. I mean, I used it, but it's nice to have a picture where you actually show that the L is the length between the 2 walls. So there it is. And guess what? That's exactly what you get for the infinite square well using the quantum mechanics equations from 1925, our quantum mechanics. So that is awesome. Now, sometimes authors like to use h bar. Now, h is equal to 2 pi h bar, because remember, h bar by definition is h over 2 pi. We saw that earlier. So if you wanted to do it with the h bar, you get 2 squared is going to get you 4. So that's going to knock down that 8 to a 2. And then here, the n squared will still be there, but then you'll get a pi squared and an h bar squared. And then you'll have here an m l squared. So you sometimes see it in that form. So we're putting in for the h, 2 pi h bar, and squaring it. So you get, this is going to be 4 pi squared h bar squared. So the h bar squared is there. The pi squared is here. The 4 cancels the 8 to get to a 2. And then you have your ml squared and you have your n squared. So sometimes you see that. So here's what we have for the energy. And if you're looking at a wave in here, some general case, I mean, we could just, well, let's just take the first case here. And this is going boing back and forth. This is your distance L. That this wave, x and t, is really, some amplitude. So this is your amplitude, your measure from the bottom to the top. This would be your amplitude of your wave. And this is a sine of kx. Remember the wave number, if it's 2, if k is 2, then you'll have 2 wiggles in there. But then when this is wiggling down, this is wiggling up, going back and forth. So I'm going to hit this with a cosine of omega t, since we know that our frequency, is f. And remember, when we have a cosine of omega t, that is a time dependence that will make this thing go oscillate back and forth. So, and you want the omega, because then when the t is in there with the omega, then you're going to get 2 pi, which is going to be like 1 cycle. So we want omega. So that is the equation that describes what this is. Now it's very neat to see that this is actually can be thought of this is called a standing wave, by the way. It's like a wave that has this pattern wiggling back and forth. But if you take a right and a left wave, say with half the amplitude, in other words, here is sine of kx minus omega t going to the right. And if I take here sine of kx plus omega t, going to the left, then remember these formulas that we derived earlier? And I'm just going to write them down from the previous class. These were derived when we were playing with the rotation matrix. Now, if you make the b minus, since the cosine is an even function, nothing happens here. But since the sine is an odd function, then the sine becomes a negative. And you get that. So let's just see what happens for fun here, because this is a wave traveling to the right and a wave traveling to the left, the same form of the wave. Okay, if we add these together, we're saying that the kx is the alpha and the omega t is the beta. All right. So you got an alpha and you got a beta. And here you're adding them and here you're subtracting them. So if you look at these things here, you can see that these two are going to cancel. In other words, this one's going to cancel that one. It's a minus sign, a plus sign. So in other words, we're going to get, and since we have a half, 2 halves will be a whole, we'll basically have this. But what is this? This is kx, and this is omega t, but that's what I got. I mean, that's what it is. So in other words, I set that up by just using the wave number to have the various sine functions without the t, and then I put the oscillation in there because it's going to make it go up and down. As t grows, it's going to go up there and then come on back down. And then I showed you that that's the same as having wave traveling to the right and a wave traveling to the left, and they're interfering to get a standing wave. Okay, we're ready now to find the Schrodinger equation. And this is Schrodinger, Erwin Schrodinger. We want a differential equation of which this is the solution. That's what we're going to do. All right, and this approach. Now, this is no way the traditional approach to quantum mechanics. I mean, this is, remember, my way of showing you with derivations in quotes, not official derivations, but help to understand physics from a holistic point of view and not to duplicate what you get in regular courses. So our theoretical physics course takes a different slant here. And we're going to derive, with quotes, all right, the Schrodinger equation, the equation for quantum mechanics. So let's write down here a reminder that there are n solutions, the harmonics on the string, and this is A, and this is sine of kn(x), and then there'll be a cosine omega t. On second thought, I don't think we need that. I think we can just do this. Let's just keep it simple. This is fine. Let's just use this one. So, if you wanted to take derivatives, but what are we shooting for? When you take the derivatives, what should we get? We should probably remind ourselves what is the equation that involves, k and omega. All right, so let's now review some stuff. We know that P is h over lambda, and if I go here with, let's say, I want to put here, I know K is 2 pi over lambda, so 1 over lambda is K over 2 pi, so that would be K over 2 pi. So I get this equation, this is h bar K. So I have an equation that is going to be useful, that P is h bar K. Now I know that my energy, I'm going to use the h bar omega. Remember with Einstein, we looked at this equation for light, but now we're going to say this applies in general. Like there's a matter wave, the momentum is going to give you a wavelength. In other words, here, a momentum is going to give you a wavelength, and then an energy is going to give you a frequency. All right, so the frequency is E over H. So just like you have a momentum in a particle, use de Broglie to get a wavelength, and we have energy with the particle, but we're going to use then this equation. You can think of these as being inspired from light. We're saying they're going to apply also to the particle. Okay, so that means we have these two equations. E is h bar omega. That's an important one. And P is h bar k. And what needs to be true is, for this case, P squared over 2m, which is my 1/2 mv squared. So this is going to be h bar squared k squared over 2m. So I need to have this be true, but remember, this is also h bar omega. So a key equation I need is h bar omega equals h bar squared k squared over 2m. That has to be true. So I start taking derivatives, this is going to be relevant to bear this in mind. So if we look at this this wave here, and we'll go ahead and write it down again, x and t, say a sine of kx cosine omega t. If I take the two derivatives with respect to x, a is constant, cosine's constant. I need the second derivative of sine of kx. Now, when you take two derivatives on cosines and sines, remember you get the same thing back with a minus sign, and you'll pop out that k twice. So this is going to be minus k squared sine of kx. Now, if you want to do it step by step, you can. One derivative will get you k coming out with the cosine of kx, and then the next derivative would pop out the k squared, but there'll be a negative because of the cosine goes to a negative sign in the derivative. So you could do it like that. So you get the same thing back. So that means the second derivative of the wave function with respect to x is minus k squared times sine, the same thing. Now, if I do, say, one derivative with respect to t on the wave, then what I'm going to do is, this is a constant, a sine of kx is considered a constant, and the derivative of the cosine is going to be negative the sine, and I'll pop out an omega. See, now we have a problem because we want the omega. We have the k squared, we want the omega, we set things equal, but now we don't have the same thing back. So we don't have the equation of which that's the solution. We got ourselves a problem. This is a big problem here, all right? So I really have to get the same thing back, and I could finish the problem. That'll become very obvious to y'all when I finish this out. You'll see how it works. But see, now something we can do, what comes to the rescue, is the imaginary number I. Because if you had something like E to the minus or plus, let's just say, we'll say minus like this. If you had something like that, if you took a derivative, you would pull down the minus I, and you would get the same with the omega. You would get the minus I omega and the same thing back. Now, if you want to say plus there, you can say plus there. We could just say, because it works for both. You could do that if you want. See, that's going to solve the problem. And if I write, say, equal, say, a sine of kx, and I'll go ahead and use the plus one here. But now, you see, if we played that game and we played the same game with the space, we would have, say, we have plus or minus ikx, and see here, and technically you have a plus or minus I omega t. And now we got to be careful. In fact, Dr. Perkins and I wrote a paper to help explain why you need to be careful. And to get, say, a function kx minus omega t that works safely, it's best to use a plus ikx with the minus I omega t. And then to get the function that goes the other way, it's best to put the minus sign here, because see, the main thing is the relative signs have to be the same, and to keep the minus sign on the right. Now that's a subtle thing, and a paper I wrote with Perkins is basically justifying that this is the tradition, this is what people choose, and really you have the freedom to choose this. You can think of it that way, that if I want to have a relative sign between the two of these, I got it. And here's a relative sign, the plus and the minus. And here I want the signs to be the same. Well, I can do that by making them both plus or by making them both minus. So we like to make them both minus so that the time dependence stays the same and the direction is reflected in this fashion. All right. So you have that degree of freedom. We can make that choice. And that choice, though, is a very good choice, and it's a safe choice to make. So where are we? Well, let's go back and simplify a little bit. And we agree that we're using the minus sign for reasons why I explained. When you put the exponentials here for the space, we already explained that that's going to work. Now, if you take the second derivative with respect to x, then you don't worry about, over here. Well, actually, if you did that, we could just go ahead and do that. You get then a, and you get minus k squared. The sine of kx comes back, and this just hangs around. But this is saying minus k squared times everything. Now, if you take one derivative with respect to time, then you pull down the minus I omega, and you get the same thing back. But see, now you can get it. Because you want is h bar squared k squared over 2m. That's what we want. And we can get that. We can get that if you look at these two things here. We're basically here, almost there. If we take this top one and say multiply this by minus h bar squared over 2m, like this, then this is going to get me here a plus sign, h bar squared k squared over 2m times the same thing back. Now if I take this one and multiply by I h bar on this one, Then on the right side, I h bar, well, I'll have negative I omega times I h bar with the psi. These will give a minus sign to cancel that minus sign, and I'll have h bar omega psi. So see, by setting these equal, I got it. I got this. That's what I want. So that means the equation, the differential equation, has to be this one. I just set these equal on the left-hand side because I know when I do the derivatives, I will get the same thing back, which I can then factor out. Because see here, when I set these equal, this is going to imply I get these, which is h bar squared k squared over 2m psi. Actually, you would, if you do the left side, you would actually get, the left side would be over here. This would be h bar omega psi. But see, then if you wanted to, formally mathematically say, I got this here minus h bar omega, and put the psi there equals 0, and then say, look, this is 0, and that gives me h bar squared k squared over 2m equals h bar omega, which is p squared over 2m equals e, which is what I need. So in other words, this differential equation does the trick. It gets us the function that we wanted for the solution. But now for the full equation, since energy equals p squared over 2m plus potential energy, then what we should do is we should put the potential energy in there. So if we do that, then we'll get the equation IH bar, the partial sign with respect to t, is minus h bar squared over 2m, second derivative here with respect to x, plus that. So then when we do everything, we'll get the usual thing up here, but now with this, multiplying the psi, you would actually have the plus, you would actually have this on with this term. You would have a plus v psi here, and if you have then the plus v in there, the plus v would be there, and the plus v would be there, and like you would have this equation checks out. So this is the Schrodinger equation in one dimension. And then what folks like to do is say, suppose the potential energy, which in general can have a function, be a function of time, say it's just a function of x. If it's just a function of x, then what we do is we can consider this function as having two parts. In other words, this part and a time part. Now, I should show you that that's going to be fine. Okay, we have the Schrodinger equation in this form, and we're going to take the case where the potential is just a function of x. It's a time independent, that the potential is not going to change. And if we do that, we're going to look at the standard mathematical separation of variables. We're going to show that we can write this form that we had earlier, where we had this time dependence with the x. We're going to show this is justified, again, by working it the other way. So here, if I look at applying this derivative, when I take the derivative with respect to t, what's going to happen is I can pull out this function since there's no t in there, and then I would get minus I omega, and I would get the same thing back. On the right-hand side, since the t can be pulled out. I'll have here minus h bar squared over 2m, and this will be the regular derivative since there's only an x now, dependence. And then finally, there'd be the v, which is only an x, v of x, and then the wave function is this one. We just plug that in here. X dependence, like this, t dependence. And see, this is going to cancel out. And I and minus I is plus 1, so you'll have h bar omega times psi is equal to minus h bar squared over 2m, the second derivative, plus Vx times psi. Now, since this is the energy, we can write this as minus h bar squared over 2m, the second derivative with respect to x, plus v of x, psi of x, equals E times psi of x. And this is called the time-independent Schrodinger equation, since the potential doesn't depend on t, and you get a simpler version. And let's just go ahead and write down again the first one that we had, which is the time-dependent version. So there are the two. Now you may want to do 3 dimensions, and for 3 dimensions, you're going to basically have your 3 partials. And we already saw that this is del squared on psi. So that means we can write the equations as minus h bar squared over 2m. Let's do this one first. And then have del squared on psi plus v on psi is E on psi. That's a 3-dimensional version. And then this one would be, and I'll write, let's write this on the left again, like this. And then this one here. That's it. The F equals ma of quantum mechanics. Now you can replace this with those 2 equations, the Schrodinger equation, time independent, time dependent. Or you can just use this one, since when v is not a function of t, this one reduces to this one, so really that's the one that you want. There is a cool trick to get the Schrodinger equation from kinetic energy plus potential energy equals total energy. And let's say we're going for the 1 in 1 dimension here. What you do is you can put the wave function on the right-hand side of both of those, and then what you do, so let's go ahead and do that, p squared over 2m plus v equal here E. And then what you do is you let E get replaced by IH bar, the partial with respect to t. And if you do that, bam, you'll get this piece right over here. Then if you let P go to minus IH bar at the partial with respect to x, then when you have p squared over 2m, that'll become 1 over 2m. And when you square negative I, you'll still get a negative 1, so you get negative h bar squared. And then when you're squaring this, the interpretation is you're applying it twice, so you're taking the second derivative. And when you do that, you are going to get this piece. And if you want to write this in vector form, you could say this goes to minus I h bar into the del operator. Now it's nice that we have picked here a negative and a plus, because remember the convention in special relativity to have this the space and time to be with the minus sign. Now this isn't relativity. This equation's classical energy equation. This is not a relativistic equation. Schrodinger tried the relativistic equation, using our little triangle with the E squared and the P squared and all that. So he tried that and didn't get the right energy levels for the hydrogen atom. So he tried this one and it worked. The Dirac equation handles the electron in a way that brings in relativity and quantum mechanics. So here, the Dirac equation will do that. So we're going to be in this realm down in here with today's class. But we'll be doing Dirac at a future date. All right, this is a remarkable achievement for someone that is a sophomore to see the Schrodinger equation here. So this is very, very nice conclusion for today.